Hello guys, first of all I want to welcome you all to my YouTube channel Cocktail 2. Today we are going to see how to do computational fluid analysis over 3-dimensional convergent divergent nozzle. Yeah, this video provides a basic knowledge in CFD analysis, so don't miss it. Before going to our session, I want to give a short intro about myself. I'm Vignesh. Basically, I'm an aeronautical engineer and working in product development domain. I have 3 years solid experience in CFD, FEA, product development and design. This is my first video in educational background, so I need to support, man. And English is not my bilingual language, so please take my apology for any mistake I have made on this video. Let's go for our session. Actually, I already created the CAD model of our Convergent Divergent Nozzle, like CD Nozzle. This is our CAD model. See, this model was generated based on MOC, like method of characteristic. And if you want to check the dimension, you can check from here. This is the basic dimension of our CAD model. You can refer from it. And which is generated in SolidWorks. You know from it. And now we can go for our CFD modeling. Just opening the Workbench, Ansys Workbench, and we go and one thing in this video we are going to do the CFD analysis with CFX Solver. So click the CFX Solver. These are the section we are going to do step by step to perform our simulation. First of all, you need to generate the geometry model in the CFX Workbench, CFX Solver in Ansys Workbench. Just to open up the geometry section. It's starting. See here, starting design model. It's taking little bit seconds. It's still opening, man. Now it's okay. It's opened already. I just copy the respective folder of my CAD model. Copy that one, and then just importing the CAD model in design model. Here just click the file, and there is an option is the import external geometry file. We are already in the file location. This is our CAD model. This is the stuff file. I'm going to import the stuff file in design model. Just click it and open. Now model is imported successfully, and we need to generate the model to display over the design model. Just generate it. Now the CAD model is performed over in design model. This is our CAD model. See, the convergent section, and it's the divergent section, and also we have done some fillet for smooth flow section. See here in the end of the divergent section also we have some fillet part is there. That's why it show variety of rings, edges. And we successfully imported the CAD model design model. And we need to check the share topology. Actually, for this model, share topology checking is not necessary, but if you importing some kind of assembly model like two or more component connected together, means we compulsory check the share topology to check the interfaces and the connection joints and the overlay of the CAD model. The main purpose of checking the share topology is to enumerate the geometric error, whether the geometry is correct or any error is there. So for that only we are checking the share topology. I'm just click the share topology, and I'm going to generate the share topology. It's ready. See here, the green icon is show. It's if our model is well find. If unless the green icon, if you show any other like yellow color or red color, means there is a problem in our geometry. So now we get the green tick, so it's not a problem. Our geometry was perfectly alright. Now I'm just to close the design model and go to the mesh section. Just click the mesh section. It's starting over here. we have to wait a couple of seconds. It's opening. It's opened successfully here. See, our model are successfully imported in mesh section. So now we are going to give the mesh parameter. I'm going to choose, this is a basic simple model, so we don't want to go any complicated mesh methods like hexagonal, tetrahedral, sweep method, so that one. So I'm just simply switching the automatic mesh method. Just right click and insert the method type. We need to select the geometry or the section. So for that I'm going to click the boss section. I'm going to click body element. See here, just click it and click the model, just apply. Yeah, we have selected a complete body of our CAD model. So we are choosing the automatic method, so every other things are default section, so no problem with that. And also for find appropriate mesh, I'm going to include edge sizing method. So for that I need to select the appropriate edges for our mesh study. So just click the edge icon and select the important parameters of our CAD model via edges. See, these edges are most important things. Inner and these sections, just zoom in and click those edges in the throat area, and oh, mistakenly I clicked this, no need of this one. Just click the outer ring, and also we need to click these edges. Yeah, fine. Similarly we have to click here, and also another important thing is we need to select the throttle edges. Yeah, throttle edges. Yeah, now I hope I have selected all the edges. Yeah, fine. Just now we already clicked all the necessary edges. Just right click the mesh section and insert edging. Yeah, this is the parameter we need to give. We have selected 18 edges, and there's a type is the element sizes. There are three different types is there. One is the element size and the number of division, sphere of influence. Now I'm simply giving element size. I'm going to give the element size as 0.1 meter. Yeah, see, the grid line are showing. See, is highly sufficient for our CAD model. If you further reducing the size means it will close together the message. See, it's very fine. So we know we don't need that much of size reduction. So I just simply put 0.1 meter. Yeah, it's highly sufficient for this model. But if you go for a complicated model, we need to refine the mesh, because then only we may get the accurate result. For this case, 0.1 meter is sufficient, highly sufficient. Okay, and we need to further select the mesh parameter in the mesh section. See, physics preference of CFD as well as solvers also CFD, and sizing. In that, see, there are several options there. I'm going to use advanced size function as proximity and curvature in order to get appropriate mesh parameters. So in relevant center, just coarse mesh is enough. And in smoothing, I'm going to put a high smoothing section, and the transaction also go fast. In smoothing also, the medium size is enough. No need to give that kind of stuffs. After checking the mesh, we can, if necessary means, we can include the other things. Yeah, other things are default, so no need to touch those things. Well, and the inflation option is also smooth transition. Everything is quite well. Now I'm going to generate the mesh. Generating. It's taking a little bit time. Yeah, it generated successfully. The mesh looks good. Yeah, it's fine. It's sufficient. In order to check the cut section of this mesh, you can select the parameter of section plane. From that, click the new section plane icon and draw any line between the model. Just click and rotate it. See, this is the inner side of the inner mesh section of our CAD model. So it's highly sufficient. So unclick the one and close it. Okay, this mesh is fine. If you want to check the mesh parameters like elemented and elements and nodes mix, we can from statistics section. See, the nodes, total number of nodes is 50,902 and the element is 477763. If you want a detailed mesh report, you can get from the mesh report preview. See, other lots of things is there. Each and every parameter of graded improvement study is available here from top to bottom. See, everything is there. Up to mesh control, everything is there. This is the complete mesh report in the section. So the mesh part is completed. So don't worry about anything, because successfully completed the mesh section. And now we are going to do a CFX solver. So in order to we need to give a initial boundary condition like inlet outlet section. So for that I need to segregate this model as 3 different parts. I mean it's a subdomain for our boundary condition. So just click the geometry file and click the face. Then click this face as we are going to include the convergent section of inlet. So just right click this and create name section and give a name as inlet. This name does not going to affect any kind of progress in our upcoming CFX solver, but if you give the correct name, it is very easily we can identify where okay this is inlet. We are going to give the boundary condition as like that. So that's user friendly. So for that only I am giving the detailed name as inlet. So for that we can easily identify it in our solver section. So that is fine. Now I am going to put this as outlet. Just right click and create new section and put the name as outlet. Hit OK. See here we have already generated named as the inlet and our outlet also. Now we are going to generate the wall section. So for that, click the face section and select all other parts like in our CAD model. These things. Each and every face of the outer parts choose. We are going to choose as a wall. So just right click and create named section and give the name as wall and hit OK. Yeah, now our model successfully enumerated in section. See, this is inlet, this is outlet, all other things are given as on wall. Okay, that's fine here. Just update here. In order to update in Workbench, just open that. Yeah, we have completed 2 subsection as geometry and mesh. Now we are going to for our CFX setup. Just open up CFX setup. Meanwhile I am going to close this mesh section because it takes too much of memory from our system. So just to close the mesh section, and now we are going up for CFX pre-processing setup. Yeah, it's opening. See here, it's starting. Okay. Just maximize it and see our model generated here. Now we are going to give going to set up our complete model in for the essential simulation from top to bottom. See, these are the basic models of a CAD model. See, variety of things you may check from here. This is inlet, this is outlet, and this is wall section. So this is fine. We are now going to do anything in this one. This is a complete model. I'm just going to rename the default domain as CD Nozzle and hit enter. Okay, this is a flow analysis section. In simulation there are several parts. The most important parts are analysis type and the solver. These are the most important parts in this simulation. Not only this, enter CFX process. These are the important parts. From that only we are going to given the boundary condition based on our appropriate requirement, as well as the solver types. If it is any assembled model or any contact surface, we need to provide interface things. So those things are involved in interface section, but we don't need anything in this model because it is a simple model. We don't have any connection here, so just we have one part only, so it's not a big deal for us. Just I'm going to give a boundary before going to give the boundary condition. I'm just to click the I'm going just to select the analysis type. Just double click it and option. This multi-field coupling, we are not going to do any multi-field coupling, so just give the option as none. And the analysis type, there are three different analysis types: the steady state, transient, and transient load. We are not going to do any time step analysis or any steady flow, so we are going to do the steady flow condition. And so for that I am going to select steady state and click apply, then OK. We have already selected the analysis type. Now I am going to give the essential boundary condition in our model. So double click the CD Nozzle, I mean the domain, and in that there is a various option is there. See, there's our type of domain. We are going to do our model in constant air velocity, constant air density. So for that that's a fluid medium. So don't choose anything any other thing unless the fluid, just if the fluid is enough, highly sufficient. And the option of our fluid is the constant air density at 25 degrees Celsius of atmospheric condition. So we don't need to do any changes in this one. And the option is the continuous fluid, so no need to worry about anything. So all other things are fine. It's a non-biased model, so no need to change anything here. And the domain motion is the stationary, so don't worry to change it into rotating, because we are not doing any rotating domain here. We are just doing the flow analysis over the like a pipe section from converging to diverging. So we don't want to give it a rotating type model, so this is highly sufficient. And now we are going for fluid models. This in heat transfer I'm going to choose as isothermal. And the turbulent, we are going to do a turbulent model, so I'm choosing the K epsilon model. Yeah, see, there is lots of model is there, like SSD, yeah, CSS stands for BSL Reynolds stress, SSG Reynolds stress, and also even laminar. We are not doing the laminar flow here, so we are going to do the turbulent model K epsilon. So I'm going to click K epsilon, and the wall function is scalable, so don't need to change anything in that. We don't need to do any compression or thermal radiation, so don't want to do anything. So I'm just to put the none. And the initialization, if you want, this is not necessary here. See, if you want to do means it's quite well, but it is not compulsory to do the initialization. But I'm going to give the domain initialization. The velocity type is Cartesian, and the static is automatically. Just okay, everything is fine here. Just apply it and okay. Now I'm going to give the essential boundary condition based on our model. So just right click our domain like CD Nozzle and insert the boundary, and going to named as inlet section, yeah, and hit OK. We already created the boundary domain in our mesh model, so for that the location is already chosen in as inlet. If we forget to choose the boundary conditions in the mesh model based on our appropriate model, means we have to choose here. So for that they never named us here, so for that we need to select the appropriate location. For us it's not a big deal, we already selected, so don't worry about that. The basic settings, the location inlet and the boundary detail. We are going to do a sum. I'm going to do it is the total pressure of inlet. Just I'm going to give the initial pressure condition as 3 Pascal, e power 3 into e power 5, 3 Pascal, and we are taking inlet as pressure inlet. That's why I'm going to give the total pressure. If you choose any other model like the velocity inlet and pressure outlet, that's quite well, but in this case I'm going to choose as the inlet as pressure inlet and the outlet as a pressure outlet. So I'm giving the option of inlet is total pressure, and I'll already give the value of 3 Pascal, and the source, there is a boundary source is no need to give the source here. If you give me, it's no problem in that. The source I'm already selected the condition of continuity. Now plot option, no need to worry about these things, just apply and hit OK. See here, our inlet boundary condition are appropriately given successfully and hit OK. Similarly, I'm going to select the condition and put named as outlet and hit OK. Like already I said the same way, the location are already selected based on our mesh domain, and the boundary condition I'm going to do is the static pressure. I'm going to give the static pressure 0 in the outlet, and the source is there, and just hit it and then retain the plot option. Don't worry about that, just apply it. See, both the inlet and outlet are selected successfully, and we're going to give the wall function here, this inlet, and push the boundary as the wall, name the boundary as the wall, and hit enter. The wall are already selected based on our mesh domains. In the boundary details, I'm going to choose the no slip wall condition. There is 3 different types of wall condition in CFX: free slip wall, slip wall. We don't need to about that. We don't want for our case. So just put no slip wall, and the wall's roughness is a smooth wall only. So no, and if you want the boundary source, just click it and apply it. Hit OK. We have successfully selected the boundary condition of our CAD model and the solver. In solver, I'm going to click the solution units to check whether our units of our CAD model are appropriately given or not. The length units are given as the meters, so don't worry about that. And the time is so in this case the length is very important. So if I already given as the meter only, our CAD model also defined in meter only, so no problem with that. If you may want to check that, we can check here. See, our CAD model are chosen as the MKS, meter, kilogram, second. So don't worry about that. We are going perfectly. So just hit just close this one, and we want to give the solver control. I'm going to choose the option as upwind, so don't need to do high resolution in that. We don't want that. Just to give the turbulence model as of I'm going to give the high resolution in our turbulence model, and the convergent control I'm going to give the maximum iteration as 500 is sufficient, I think, because it's simple model. It may be converged before the 100th or 200th iteration, because we are choosing the post mesh itself. So don't worry about that. Don't want to go the further iteration, because it will converge within 500 iteration, because it's a very simple model. And the residual type is RMS, we are root mean deviation works well, and the residual target also e power -4, and the equation is continuity, momentum, turbulent dissipation, these are the basic essential equation settings in our model. And these things are advanced. We don't want to go this, because we want that kind of advanced model. We just do this section. We already given the solver control, basic solver control for our requirement. So we need to go the advanced section. Don't want to go the advanced section. That's output control. Everything is default for here. Just close it. We have given anything. The material option is there. We already given the RS 20 fluid as air at 20 degree. See, just apply it and hit OK. Now we have given everything here. every essential thing. I hope, yeah, we have successfully provided essential data of our model. So this is fine, just to save it. I'm going to choose the appropriate location, choose the folder path, and save the file as CD Nozzle. And save. Saving C here and here. So the setup was completed here. I'm just want to open the solution. Just CFX Solver Manager opening here. See, starting. Yeah, I'm going to give the run definition of double precision parallel environment and hit the file. This is the my host name, that means my computer name. So that's highly sufficient for here. Now that's to start run. Yeah, it's gonna induce the simulation for our model. It's taking a little bit time because I have lots of stuff in my laptop. Yeah, it's gonna start. Our model is starting successfully. See the accumulated time save as well as variable value, the continuity, momentum, everything is there. UV double velocity of the model. See, our model are going to performing now. I hope it will converge around 100 or 115th iteration. I hope, because it's a very basic model, and also we give the mesh condition as very less only. That means coarse mesh only. If you choose any instead of coarse mesh, if you choose any fine mesh, it will take little bit computation time. So for this video I'm just created for learning purpose only. So for that I'm just choosing the coarse mesh. But if you if you comes around any complicated model or any complicated model in edge section, if you have lots of bend in your CAD model, means it's a little bit difficult to enumerate that one. So for that we need to give the mesh parameter appropriately in each and every section. For this model don't worry about anything, because it's a very simple model. So for that it's highly sufficient for our mesh requirement what I have given earlier. Yeah, our model performing it now. It's 18th iteration completed. I think it's take little bit time, so I don't want to run the recording here. So I just want to pass the video here, and until after converging I just continue the recording. I just want to stop this my recording. After converging I will continue my recording. So I'm just going to pass this video, so please wait patiently. Hi guys, welcome you all again. Like I said already, our solution was converged. See here, was completed normally, and it was converged at the iteration of around 85. Yeah, our solution was converged at 85, because I already said it's a very simple model. It will converge quickly. Yeah, see how the convergent curve. Now our solution was converged. Now we are going to do the post processing. Yeah, just to save the file in the Workbench. It's saving now, and just to close the other things like the CFX Solver as well as the CFX setup. I'm just going for post processing. Yeah, just double click it, and it's starting the CFD post. And CFD post processing is one of the art. Yeah, from that only we are going to deliver the good quality of result to our client. What are the works we have done, what are the results we have get from the simulation. This is the most important part of the entire CFD analysis. We can deliver simulation result in perfect manner. Yeah, see, this is the wireframe condition, wireframe of our model. Just click the inlet and outlet and wall. See, this is our model, and I just hide the inlet and outlet. I'm going to change the transparency of our model. Just double click the wall, and if you want to change the color, means you can change the color of the model. And now for me it is highly sufficient, so I don't want to change the color here. Just click the render option, and see the transparency is there. You may give the transparency as well. Just click anywhere around here. You may check the transparency case. Just apply it. Yeah, 0.5 like this. I think it is highly sufficient. Just apply it. Yeah, this is the transparency of our model. And this one is on off. If you want to hide the outer edges of wireframe, means you can unclick the wireframe. For perfect visualization, I want to click this one. I want to disable the wireframe, and now I'm going to show the result of our model. So for that, we want to do the contour section as well as velocity vector, as well as streamline path, and how the flow was moving from convergent to divergent section. These things are going to do in our post processing. Just want to click select the location, and going to create the plane of our model. Just to click the plane, and I'm going to create this plane as in XY plane. So I want to name the plane as XY plane simply, and hit OK. So here our model are going to create, and our plane was going to create. So just in method, click the XY plane, just apply it. See, we have created a plane in XY plane. Similarly, I want to create a plane in XZ plane. Likewise, same things. Just click location and plane. Give the name as XZ plane, and hit OK, and change the method as XZ and apply it. See, I have already selected the XY plane and XZ plane. With the help of this plane, we can deliver the contours of our simulation. So just click the contour section here and give the name as velocity contour in XY plane. Why I am naming in perfect manner means, it will give me the easily I can identify easily. If you just click velocity 1, velocity 2, any other name, means it is very difficult to find where is the velocity contour is there, where is the pressure contour is there, where is the temperature contour is there. So further only I am each and every section I will give the appropriate name for our better understanding and identifying the contours. I already selected the one, and then I am going to choose the location as XY plane and the variable as velocity. Yeah, just apply it. And for perfect visualization, I want to hide the planes of our XY and XZ. So this is our velocity contour for XY plane, and I want to give a perfect contour for this. This is only the long is value is there. I'm going to give us 250 for appropriate view. Just hit apply. Yeah, now you can see the velocity contour in perfect manner. Just right click it, and I want to change the view as view plus Z. Yeah, see, this is the velocity contour of XY plane. You may identify from this the velocity is maximum order product is the criteria of flow result appropriately fine, I hope. And the maximum velocity is see 1.9 into 10 to the power of 3 in throttle area. Similarly, we can create the pressure contour, temperature contour in easy manner. We don't want to Go again to select the contours and name the velocity contour on XY plane, blah blah. No need to worry about that. Just right click the velocity contour of we already created and duplicate the name as I'm going to pick a contour now as pressure contour. So I want to change the name as pressure contour of XY plane. Just hit OK and yeah, it's already created. See pressure contour and I have hide the velocity contour of XY plane. In pressure contour, the the variable already given us the velocity. I'm going to change the velocity into pressure and apply. See, this is the pressure contour of our simulation. See, the pressure is minimum in the throttle section. As we all know, the pressure and velocity are inversely proportional. So here the in throttle section the velocity is maximum. Likewise, the pressure is minimum at the throttle section. So we get a theoretical proof for our model. The pressure is minimum in the throttle section and the velocity vice versa, the velocity maximum in the throttle section. So we have picked the velocity contour and the pressure contour in XY plane. Likewise, if you want to generate velocity contour in XY plane, just simply I already said, like, right click of the pressure contour and duplicate the name as pressure contour XZ and hit OK. See, it's generated and unhide the pressure contour of XY plane and click the pressure contour XZ plane just to change the location, yeah, from XY to XZ and apply. See, we have created the contour of XZ plane. This is XY plane. Yeah, in both one we have generated successfully. Similarly, we want to generate the velocity contour in XY plane. It's just simple. Just right click the pressure contour in XY plane and duplicate the name as velocity and hit OK. Likewise, unhide the pressure contour next and double click the velocity contour and change the variable from pressure to velocity. See, this is the value for the contour for XZ plane. This is the velocity for XY plane. See, this is the velocity contours. So we have done the you may identify how to do the contours, how to pick the contour from the model. It's a quite simple, right? Similarly, if you want to check the contours or the velocity path in YZ plane, means you need to generate the plane in YZ, like from here to here. So you can do it from what I have done earlier. Likewise, we have to do in OEZ plane. So I don't want to do you may practice from your what are you saying, from your system. Yeah, now you are going to understand, you already understand how to generate the contours, so it's fine. Now I'm going to do is how to generate the velocity vector. Just hit the velocity vector and change the name or give the name as vector XY. Just hit OK. The location, similarly, we may generate from any of these things. See, I am going to select the XY plane and apply it. See, for perfect visualization, I want to change the view and unhide the wall and also unhide the wireframe. See, this is the velocity vector. See the flow path. If you want to change the factor, it will looks fine. Just give it 2 and apply it. It's reducing. So no, one is already fine. Just click apply, and there's a variety of options there. See, the symbol is there. We don't want to the line arrow, means just to change from arrow 2D. That only the 2D is there. If you want to increase the size, means you can increase from here. See, I already said nah, the post processing is hard. You can do it from anything from here. Instead of 2D arrow, I'm going to give a 3D arrow, and also I'm reducing the symbol size and apply it. See, if we zoom it, means it will looks fine. Yeah, but there is a little bit screen, so I can't unable to give a exact visualization. And also there's several options. If you want to the ball section, just click the play one. This is the ball section. It's horrible, right? It's quite funny. I just reducing the symbol size and apply OK. See, you may check from here. You can see the velocity is maximum of the throttle section, as I already said earlier. I don't want to go for any other section. Just hit the line arrow and hit apply and increase the symbol size. Yeah, this is the method. Likewise, only we have generated the velocity vector. So this quite well, right? So you can do it from likewise from I already done earlier. So just hit the velocity vector of xy. Now hit select the wall for our perspective visualization. And now I'm going to do how to do the streamline path. See, just select streamline path in xy. Just hit OK. There are two types of streamline path. One is a surface streamline and the 3D streamline. First of all, I am going to show the how to do a surface streamline. Just click the type as surface streamline, and in surface I'm going to click the xy plane and apply OK. See, for a perspective view, I'm going to change the view as first user. See, this is our surface streamline. I'm going to increase the points like this. Yeah, just get this one. This is our streamline path of xy plane. Likewise, I will show you how to do the 3D streamline path. Just change the type from 3D and apply. I'm going to start from 3D streamline from inlet. Yeah, apply. This is the streamline path from inlet to outlet. There's a variety of options there. You may hide the lines, streamlines, and instead of that we can give the symbol as wall. So I already give the wall. See, the default one. I'm going to hide the line. Just hide the line and apply it. See, there's nothing is there, right? So in animation view it looks fine. See, I will show you how to do the animation things. See, I'm going to show you how to do the animation streamline path for our model. See, there's animation play option is there. Just click it and click the what the animation I'm going to do. That is, I'm going to do the streamline xy. Just play. See, it's quite good now. Flow path moving from there. It's really quite good. Just stop it. We want to view in slow motion. Just increase the frames. That means slow option and play it. See, it's further. It's slow. It's moving slowly. Yeah, you may watch it. How flow was moving from Convergent to Divergent Nozzle. See, it's very smooth flowing over the wall. Because we are already given the wall function as no slip wall. It's quite well, right? I will show you in front section. Yeah, just to close it. Change the perspective from. See, now I'm showing you the clear manner. Just to play it. See, from here you may see how the flow was moving from Convergent Divergent Nozzle. See, the velocity maximum what is when we're entering into the throttle, it moving fast. Yeah, due to the less pressure and the throttle section, the velocity was increasing. You may save the motion video from here. Just stop it and again open up here. See, they expand the icon here you may save the video in corresponding folder in which you want the video of our simulation. So these are the things we have done. It is the very quiet and the basic things, basic CFD model. You can learn from simple things from here. So I hope you may understand how to do the CFD analysis in here. So these are the things we have learned from today's session. So guys, I need your support. Based on your response only, I'm going to upload more number of videos. So please subscribe my channel for more number of video in different domain like CFD, FEA, product design and development. You may get a variety of videos. So don't forget to subscribe the channel, and if you like this video, just share this video to your friend circle. They may learn the CFD analysis, basic things, how to do the section in Ansys Workbench with CFX Solver. These things are very basic things and also very important things in non-circuit engineering branches to combine students like aeronautical, mechanical, automobile and even civil. Yeah. So if you have any queries about the CFD analysis, just comment in the comment section. I will pay for you. I will respond as soon as possible. So guys, just subscribe the channel. So for that only I'm going to motivate myself and deliver good qualities of video and also different kinds of model in variety of domains like CFD, FEA. So from you guys, from your response only, I'm going to deliver more number of video. And thank you for watching this video. Again, I'm telling, if you this is only the basic thing, simple model. Yeah, and in future I'm going to deliver the difficult type of model like rotating domain, turbulent blades. So those things are I will upload later. So based on your response, I will perform well. So guys, just subscribe the channel, and today's section was finished. And thank you so much for patiently watching this video now, and really thank you. And I'm going to sign off now. Thank you very much.